Okay, great. So thanks for having me. It's really ongoing work. I've made the discussion job really hard, so I apologize. But that also means that it's super interesting for me to present today and to have lots of feedback. So again, if you have any questions, please do ask during the talk. So I'm presenting this paper called Thirsting for Solutions. Um, Water crisis has been ranked in the top 5 risks in terms of impact by the World Economic Forum since 2012. And as you can see, it's prevalent in sub-Saharan Africa and in the country that I'm going to focus in, which is Ethiopia. So the entire project stems from the fact that access to clean drinking water remains a challenge in Ethiopia. You have around 60% of the rural population in Ethiopia that still didn't have access to basic services in terms of drinking water in 2022. Um, Basic services means that you don't have it, not having access to basic services means that you either have to walk more than 30 minutes to fetch the water or that you don't have access to an improved source. So it's both in terms of quantity and quality of the water. And so access is complicated and climate change is making it worse. Climate change is a water crisis. You have either too little or too much water. The two are detrimental to drinking water access. So if you have too little water, then it's a drought and ponds and wells and water sources on which people rely on are drying up. And too much water can also be detrimental to water access because it can damage the infrastructure, but also because if you have heavy rainfalls, then it doesn't recharge the aquifer as good as steady rainfalls. So access is complicated. Climate change is making it worse. But water is essential for human life, health, and dignity. So if people lack access to drinking water to meet their basic needs, then they might migrate. So this paper looks at the impact of drinking water scarcity on migration in Ethiopia. The climate migration has already been studied in the literature, but it has been studied mostly through the um, agricultural channel lens. That is, that you have lower precipitation, higher temperatures, that leads to a decrease in agricultural income, which increase the incentives to migrate, but might also trap people in their origin location because they lack the means to migrate. And here with this paper, I'm trying to shift the focus on this other channel that I call basic needs or drinking water channel. And I think that's important because people select into migration and the selection into migration might be different when it's closer to economic migration than forced migration. So in this paper, what I'm doing is leveraging the Ethiopian context to document patterns of wells failure. I'm using new data sets that are mWater and WaterPoint data exchange. And then I'm going to use those data sets to train a machine learning model to predict climate-induced well failures. That is going to be my shock on drinking water access. And then using this exogenous shock, I estimate the impact of those predicted wells failure on migration decisions. The aim is to not only answer the question whether there is or isn't migration because of wells failure, but also to explore the selection, as I was saying, and also mechanisms. Is it health related? Is it time use? So do you spend more time fetching the water so you have less time to farm and then less income, and so you might be trapped, and so on. So this is new and still working on it, but what I think I'm contributing to is three main strands of the literature. The first one is using predictive analytics in the development context. So you have a new and growing literature on using machine learning to gain insights on development settings. So here, I'm the first to try and use machine learning to predict wells failure. Um, then another strand is water scarcity, infrastructure, and rural livelihoods. So you have really few quantitative papers on drinking water scarcity, drinking water access. And the few that do exist look at context mostly in India or in developed countries, because it's where you have better data. So it's easier to look at those questions. And lastly, as I was saying, climate migration. So here again, the flavor I add to this literature is looking at drinking water scarcity and not only agricultural water. All right, so if there's no question, I'm going to jump into the context and data. So I use a lot of climate and geological data to predict whether the wells are functional or not, and then also in my empirical strategy. So every climate variable comes from ERA5, which is a European dataset reanalysis that uses both weather station and forecast models to infer precipitation that you can see here on the map, and temperature, and a bunch of other variables. As you can see in Ethiopia, you have a clear, distinct, two clear, distinct regions. So you have the highlands that are on the left that are really blue because there is there is more rain, and then you have the lowlands that are on the west or right of this map, where you have way less precipitations. So there is variation geographically. There is also variation temporally in Ethiopia in precipitations. You have two small rainy seasons. And I'm also, so ERA5, I use that to get information on temperature and precipitation, and also to construct an index of drought, which is called the Standardized Precipitation Evapotranspiration Index. It's a classical drought index that allows you to combine information on precipitation and temperature. So it's a water balance measure, and I'm computing it at the sub-basin level. So it's a sub-basin, hydrogeological sub-basin is the region in which all of the water is going to flow in the same place. And so I'm constructing this measure of drought at this level. And as you can see, again, there is variation both geographically and temporally. So the A figure shows the SPI in 2010 and B in 2015. And you can see there's a drought coming in the eastern, southwest, part of Ethiopia in 2015. Then I'm also using groundwater data. There is a few data sets on groundwater in sub-Saharan Africa. The two that I'm using are Fan and Bonsor. Those are not varying across time, so it's an indicator of groundwater depth at one point in time. And as you can see, there is some the two data sets don't agree. Fan was built globally, so there might be also it might predict less groundwater depth in sub-Saharan Africa compared to Bonsor et al., which was constructed for sub-Saharan Africa. I also use Pelletier et al., which is a new data set that, well, not new, but we are starting to use it. We have been starting to using it only recently. And it measures the depth to the regolith being the hardest part of the soil. And so the deeper it is, the more likely you have big aquifers, and the shallower it is, the more likely it's only small pockets of groundwater. So it is related to groundwater, but it's not per se a direct measure of groundwater. And as you can see, it correlates better with Bonsor et al., but also different measures. And then I'm linking that to socioeconomic data. I'm using the Ethiopian Socioeconomic Survey, ESS, which has 2 panels and 5 waves. So the first panel, I have 3 waves spanning from 2012 to 2016, and a second panel from 2019 to 2021. It's a panel of households, so they are tracked in time. Attrition is quite low in the first panel, so 98% of people were re-interviewed in between wave 1 and wave 3. So that's quite good. In panel 2, you have more attrition because there is a civil war that started in those years, and so some regions weren't revisited, and so you lose part of the panel, but you also have more questions on water access in the second panel. So I'm still trying to draw on those observations. And so I'm going to use this data to measure migration. I have two different measures of migration, one that I'm going to call permanent migration and another one that I'm calling seasonal migration. Permanent migration relies on the report of remaining households that remaining members of the households that someone have left the household and that this person isn't dead. So if someone left the household and is reported to have left the household, then this person is counted as a migrant, and then I'm gonna count the number of migrants per households. And seasonal migration is based on the number of months you spent away from your household within the year. And so if it's in between 3 and 6, then I call that seasonal migration. And it's going to be, yes, again, a count of the number of household members that engage in this seasonal migration and the number of months that they spend away. I'm also using this ESS data to have information on access to drinking water. So I have different aspects that are reported in the data. I have the time people take to fetch water, so water hours, which is a number of hours an individual spend fetching water. I aggregate that at the household level to have the amount of hours a household has to dedicate to fetching water. Those are based on individual reports, so it's in the time use questionnaire, and each individual is going to report how much time they spent fetching water yesterday. Then I also have reports from the household head on the time the household spend fetching water in the rainy and in the dry season. And lastly, I know what is their main water source. So what they were using mostly to get water in the rainy and in the dry season again. And interestingly, for my setting, for my questions, people in Ethiopia rely a lot on groundwater to fetch, to get their water. So then around 50% of the sample reports groundwater being the main source of drinking water. So when I'm gonna have this shock on access to groundwater, so this wells shock, it's gonna affect those people that most of the people in the sample. Okay, and then lastly, I'm using this new data on wells failure. I'm combining mWater and WaterPoint data exchange, which are two data sets. mWater originates from a startup which is trying to increase monitoring of wells in sub-Saharan Africa. You may know that there's a huge issue with maintenance of wells in sub-Saharan Africa. So lots of wells are failing, and this poses an issue for access to drinking water. And WaterPoint Data Exchange is mostly governments and NGOs reporting on the functionality status of wells. I've put two pictures of wells in Ethiopia so that you can see that it's really, you have to think of those as drinking water wells. So there are big differences in between drinking water wells and agricultural wells. You need way bigger you need way bigger wells to irrigate, and a drinking water well will not have the yields to produce or to bring up, to lift enough water to irrigate. So it's not like those wells cannot be used for irrigation. I'm going to show you also that there's no difference in between places that have and don't have a functional well in irrigation, but as a first step, just those wells are too little to be used for irrigation. And so I'm combining those two data sets to have a survey of wells in Ethiopia. And in each data set, I know whether the well is functional and at the time of the monitoring. So I'm going to have a cross-section of functionality status across the wells. So for each well, I know at one point in time whether it was functional or not. For some wells, they were revisited, and I can have up to 5 observation for one well. But it's really, really not a lot of those wells have been revisited. And for now, it's mostly I'm relying on this cross-section of the functionality status. And I have a bit more information, which allows me to have some descriptives on wells failure. And so, as you can see, community managed wells tend to be more functional. Hand pumps are also more likely to be functional. There is a trade-off in between digging deeper, so having maybe a more reliable access to groundwater, because the deeper you drill, the more likely there is going to be groundwater at all point in time. But also then it means that you need a motorized pump. But as I was saying, maintenance is an issue. And so a motorized pump is more complicated technologically. And so it's harder to repair and it's more likely to break down. So actually, hand pumps are more likely to be functional. Then the older the well is, the less likely it is to be functional, which is reassuring. You see this kink around 5 years, like when the wells are 5 years old. Based on the discussions that I had with people from the water sector in Ethiopia, this is likely due to wells being repaired. So around 5 years is usually the time where people are going to invest again in the well and try to repair it. I don't have enough information to say with the data whether that is true or not. And then looking at climate, I see that in drier places, wells are less likely to be functional. So here I'm plotting the SPI, so my measure of drought that I was presenting. And you can see it, so a smaller, so a negative SPI is a drier place. So places that are drier are less likely to be, the wells in places that are drier are less likely to be functional. The relationship holds looking at precipitation. So in places where it rains less, wells are less likely to be functional. And it also holds with precipitation lagged. So I'm lagging precipitation to try and have a measure of groundwater. So groundwater is just surface water, so rain that has seeped through the earth. And hydrogeologists say that it usually takes around 2 years to seep through. And so that's why I'm plotting this lagged precipitation. And you can see that the relationship still holds. So in places where it rained less 2 years ago, wells are more likely to be non-functional.
Lucy, can I ask you a question about that?
Sorry?
About the previous graph, can I ask you a question?
Yes.
Because you're showing us that when there's less precipitation, the wells are less likely to be functional.
Yes.
And you were showing us at the beginning that there was, you were showing us one map in which in that year there was a drought in the country.
Yes.
And then I noticed that most of the functionality of the wells was registered on the same year in 2021, I think it was. Can you tell me if the drought was also close to 2021, or because I don't remember right now, and I think that this might affect, if you are registering the functionality of the wells closer in time to when there was a drought, and you're showing us now that when there's less precipitation, the wells stop being subfunctional.
Yeah.
There
Yeah.
might be
Well,
a correlation there.
yeah, no, definitely. So, first, this is all correlational. I'm not claiming any causality here. It's just descriptives. But I agree that most of the wells were visiting in 2021. 2021 wasn't necessarily a big drought year in Ethiopia, but it definitely is affecting well, whether wells are functional or not, the climate. Well, that's the entire my entire prior, and the machine learning model is based on the fact that climate is impacting wells failure. So it's going to affect whether wells are functional or not. I'm also here drawing on every well, not only those in 2021. And even if there was a drought in some places, then in other places it won't. Not there's geographical variation. So I'm I still think that this relationship will hold. I can try and restrict, for example, to only 2021, where most of the wells were um, surveyed, and then see if there is like regions where it's not as dry in 2021. You still see this relationship, but that's yeah, a good point. Thanks. All right. And so, yeah, I was saying, so precipitation lag, the first like way to try to get to groundwater depth. And then there are those models of groundwater depth that I was presenting. So Bonsor et al. And Fan et al. And here, so Fan et al., the one on the bottom, you don't see anything really going on. It's also, as I said, the one that is built on the global data. And so it might just not perform well in sub-Saharan Africa. In the one which is built for sub-Saharan Africa, you see this decrease in functionality of the wells as the groundwater gets deeper, which is coherent with the fact that so hand pumps were more likely to be functional, and also that the deeper the groundwater is, the more you have to drill, and so it relies on more technology. All right, and then so this is interesting, but I want to link it to people's outcome, and so I want to link this data with the socioeconomic data. But as I said, I only have this cross-section of functionality of the water points, and it doesn't really match with the timing at which people were surveyed in my socioeconomic data. So what I'm going to do is leveraging machine learning to expand the sample. So in some places, I can see that they were using a well as their main water source, but I don't see a well in my data. So I'm going to be able to predict whether this well is going to be functional or not. I incorporate time varying factors. So for now, what I was describing is a cross-section of functionality of wells. I'm going to use the machine learning to predict whether each month the well was functional or not. And then this allows me to have a panel for each well of functionality. And lastly, I'm going to use only climate and hydrogeological and geological information to train the machine learning. So it's going to use the prediction can be used as an exogenous proxy for climate, for wells failure, and so an exogenous shock on water access. So the data sources for inputs, there is a lot of them. So as I was describing, I'm using ERA5 for precipitation, temperature, and the SPI. I'm also using Hydro Atlas to have information on elevation, soil erosion, lithological classes, and a bunch of other information. and the African Groundwater Atlas to have information on geological classes and aquifer productivity. So that's a lot of different variables, around 400. So I'm first throwing a lasso at it to select which variables are the most predictive for the functionality status of the well. This selects around 200 variables. Then I interact those variables and I throw another lasso at those interactions and the non-interactive variables to select again the variables that are the most predictive for the functionality status of the wells. And this leaves me with around 300 variables that I'm going to use in a random forest model. And this random forest model predicts quite well, so it's correct around 74% of the time. I'm using here both variation in time and in space to predict the functionality status of wells. So the machine learns from both wells that are in different places than the well for which I'm trying to predict, and from different point in time. So you might be worried about leakages. The machine learning predicts quite well in the spatial dimension. So if I'm splitting at the unit level, it's going to predict really well whether another spatial unit, so sub-basin, has functional or non-functional wells, even if it has never seen it. And it predicts a bit less well on the temporal dimension. So when I'm splitting across years, so using years, training on certain years and then testing on years that the machine has never seen, then it predicts a bit less. So that's an area where I'm still trying to improve the machine learning. Maybe I'm going to use only spatial dimensions and then build different models across time and use those different models every year. But then since the reporting of each well is different, since the reporting of wells is different across years, I might have some models that predict better than others, which might be an issue. So I'm still thinking around that. But reassuringly, I've talked with hydrogeologists, and the most predictive variables that you can see here are, it's not a shock to hydrogeologists that those are the most predictive ones. So you can see that it's, for example, the most important variable is going to be the interaction in between total precipitation that month and the maximum depth of groundwater in the sub-basin. So that's based on my priors and the priors of hydrogeologists, that makes sense. Then it's the SPI lagged with an index of the quality of the soil, which again makes sense for hydrologists and so on. So that's the most predictive variables are quite close to what we would be expecting. And so those are only measures of performance based on the machine learning and the data on wells itself. But I also have those socioeconomic data for which I can look at whether the predictions also show something in the real world, or in have some socioeconomic impact. And so looking at what's the impact of having a non-functional well on your groundwater use as your main source. So you can see that groundwater use decrease. So stating that you have main water that relies on groundwater decreases when wells are not functional. So that's quite reassuring. And also this last variable, which I call no water, is the likelihood of having your water source that isn't providing enough water for you in the last month. And this is positive and significant. So again, that's quite reassuring that we see those effects. Here I'm controlling for Kebele times time. So Kebele is the smallest administrative unit in Ethiopia, household fixed effects and month fixed effects. And reassuringly, again, controlling for different type of climate. So the climate first one is I'm controlling for temperature and precipitation. And the second, I'm controlling for this SPEI, so the measure of drought. It doesn't change the magnitude or sign or significance of the estimates. So that's quite reassuring. And then I can look at the impact on time to water. When it's people that report for themselves, so this time to fetch water reported by individuals, I don't see anything going on. When it's the household head that reports the time that people took to fetch water, I do see a decrease in the time that people took to fetch water. It goes with the fact that usually people take more time to fetch water when they are using a well. So here I'm plotting the time people take to fetch water based on whether they use groundwater as their main water source or not. And you can see that, again, there's this discrepancy in between individual and household reporting. But mostly what I can infer is that people take more time to fetch water when they are using a well. So wells are further away and you have to walk to them. And so when the well isn't functional, you're not going to walk more, you're going to take less time to fetch water and switch to another water source. And it's likely going to be a dirtier water source. And then I'm going to use those predictions in my empirical strategy. So I'm looking at the impact of having a non-functional well on migration, controlling for household level controls. I'm going to always show you with and without those controls, because in the climate literature, climate migration literature space, we are worried about bad controls. So always with and without those controls, and also controlling for climate. Again, Kibele times time fixed effect, household fixed effect, and month fixed effects. You might be worried that I'm only picking up differences in agricultural variables. So my whole point is that these wells failure are different from a more general climate shock that would impact agricultural yields. Here, I'm plotting a balance table in between places that have a functional well and places that don't have a functional well. And you can see that there isn't much a significant difference in between those two. So except for the distance to the road and to the population center, and places that have a non-functional well are more likely to be closer, which can make sense in the idea that if you really don't have access to another source of water, then you need to be close to another center to get that water. So if you are in the most remote parts of Ethiopia, not having a functional well is going to be really bad, because it's not likely that you are going to have water vendors that are going to come here to give you some water or other things like that. And reassuringly also, we'll see that still the precipitations are different, significantly different in between those places. It's a main predictor of whether the wells are functional or not, so that makes sense. But you can see there is no like significant difference in soil fertility or in harvest or whether people irrigate or not, which is quite reassuring in the sense that I'm capturing something that is different from this agricultural channel. And so getting to the results, here I'm showing the results on migration. So to remind you, here permanent migration means that someone from your household has reported that you have left the household, and it's not that you've died. I don't see much going on for whether you have a binary measure of having or not having a migrant in your household, so nothing much is happening here. I do see a decrease in the number of migrants. So what that tells me is that when wells dry up, you are less likely to have more migrants. So it's not on the it's more on the intensive margin and not on the extensive margin that the effect is that something is going on. I can show you the tables just to show you that the climate measure, when I'm controlling for climate, it's not significant at any point in time, and it doesn't change the magnitude um, or the sign of the effect that I'm capturing. And so that's again quite reassuring that it's something else that's going on. Then I'm looking at whether first steps into some heterogeneity in who migrates. So first steps on what's the selection into migration. I see that it's mostly happening for the effect is capturing mostly male migration, which makes sense in Ethiopia because it's more men that are migrating. So here I'm showing the number of male migrants. Since every measure is at the household level, I'm still figuring out how I can do a better job at showing heterogeneity in between gender for those measures of migration. And I don't see anything going on in terms of seasonal migration. So again, seasonal migration is the number of months you spent away from your household. And so here, the number of seasonal migration is going to be the number of individuals that stated that they weren't sleeping in their primary household for from 3 to 10 months. And I don't see anything going on, which is again, I can rationalize it in the sense that if it's a drinking water channel or a basic needs channel, then it's likely that it's not going to affect those type of migration that are really seasonal and going to happen independent of whether you have or don't have access to drinking water, and it's going to affect mostly permanent migration and more longer term type of migration. And just some first results on some mechanisms that are going on. So I'm here plotting the impact on the expenses on water. So you do see this increase in expenses dedicated to water, but you don't see difference in total consumption. So what that tells me is that you still have, so reassuringly again, the wells failing means that you have to spend more on water. Wells are mostly free, and other type of water is either going to be free if it's surface water or unclean water, or you're going to have to pay it if it's a water vendor or water truck. So that's reassuring, but you don't see anything going on in terms of consumption. So that tells me that you have this, what's happening is mostly driven by water and not like other type of impacts such as food shortages or other things like that. And that's it for me. And just some next steps, which are a lot of them still. But I want to improve the algorithms that I was saying, dealing with the leakages. Class imbalance, I have way more functional than non-functional wells. And there are some machine learning techniques to deal with that. I'm not coming from the machine learning space, and so some of them seem really wrong, such as synthetic minority oversampling, which is just duplicating some minority class observation and acting as if they exist for real. I'm not, convinced by that. Then I want to combine maybe the random forest with the KS nearest neighbor, because as I was showing you, the machine learning does way better at predicting across space than across time. So adding this to the k nearest neighbor is likely going to increase the performance of the algorithm. Then working on convincing people that the algorithm do work. I have found some water prices data in Somalia that varies across month. So I want to see whether predicted wells failure drive those prices up. They also have a monitoring network in Somalia for 36 wells, so I can see where the groundwater table, and I want to again look whether my predicted measure of wells do correlate well with decrease in groundwater table. And then look at those wells that were observed several times and how well the model predicted them. Then in terms of results, again, I do want to do more on the selection into migration. I've shown you some tentative things on gender, but I also want to look at age. I have some information on destination, so whether they went to urban or rural destination, which I think is interesting, and also the reason stated. So for not all of the observation, but for some people, I know why they migrated. And so I think that would be interesting to look at also. Again, more on heterogeneity. As I was saying, distance to road is different, like significantly different in between places that have and don't have a functional well. So I want to look at heterogeneity in terms of results in that dimension, wealth dimension too, and soil fertility index, just to make sure again that it's not agricultural water channel. And more on mechanisms, so time use. I have some starting point on so the amount of hours you spent farming, but that I need to wrap my head around. I want to look at education also and health. And lastly, I need to, so what I've presented you, the errors are clustered at the EA level, so at the community level, but I think I need to do more in terms of standard errors and in terms of dealing with the fact that my independent variable is constructed through machine learning. So either bootstrapping standard errors, there's also recent literature on dealing with those standard errors when using machine learning, and work by people here at Berkeley, Tama Carlton, for instance, and multiple imputation to try and get to make sure that the effect still exists when I'm controlling better for the standard errors. I want to look at, so I've done all this work constructing this machine learning, but it also gives me like the most predictive climate variable for wells failure. And so I can use those as a proxy in the regression rather than using the predicted variable, the predicted wells failure, and see whether that works and whether at least the magnitude is the same. And then I want to do a subsample on groundwater users, because those are the ones that are supposed to be the most impacted by the wells drying up. And that's it for me. Thank you.
Thank you. Thank you so much. This is a great presentation. Really excited to see your work. We're now going to open up for discussion. So our discussant, Carlos, is going to present his discussion. And then after that, we'll also open the floor. So we know that someone had raised their hand in the chat. So after the discussion, feel free to respond initially to whatever you want, Lucille, and then we can open the floor more broadly. Thank you.
Okay, great. Thanks.
Hope, can you hear me, I guess? Yeah, good. Thank you, Lucio, for your presentation and for the paper. It was great to read that too, as well as hearing you. I noticed there were some updates, so I feel like some of my comments might be not useful anymore, but because you will just address them in your presentation, so that's good. So I'm gonna try to focus on the big picture and then go a little bit more fast so we can have comments of other people too. But one of my major comments was exactly what you mentioned about the paper contribution, which is you are focusing more on the access to drinkable water as opposed to these weather shocks that can affect agriculture. So I missed a little bit more details on the prediction model, which you addressed. So it looks like your prediction is coming from those weather shocks. So I was wondering exactly is there any geographic reason or some other region that can cause this dysfunctional on wells that are not connected with agriculture? So how can your well not be working, but at the same time, your weather conditions for agriculture are stable and I mean standard for your production? Yeah, and I mean, this is from the previous draft that I have, but it looks like your contribution, it could be also an interaction of those non-functionality of wells together with the dry season or not. So maybe that can buy you there. But I think that here maybe update this update. But one thing that I would do also is add more outcomes. And I think that you did that in your presentation, is that add as outcomes agricultural production, or add as outcomes what the other papers that focus on weather shocks on agricultural productivity uses as outcomes in your specification, just to double check if the well functionality is not predicting that, is not causing that. Another thing that I noticed and I discussed a bit in the draft, that was how representative are all these water points that you found with those data. And at some point you mentioned that some of those water points, they are not matched with the socioeconomic survey. So there are people that report having a well, but you don't observe that in your other source. So I would say that you can use this non-matching as actually an outcome and see if the fact that you don't observe this water point with your water point data, if this is correlated with household characteristics. So how well is your water point in terms of capturing the whole sample? So are you only capturing water points that are from, I don't know, rich families and more educated ones? So maybe you can use this non-matching dummy outcome as well. Yeah. And maybe you can also map that with some population density or some other geographical water features in Ethiopia. Let me see what I have here. And yeah, it will be also helpful to understand on how representative is this shock for the population of the country. So my understanding is that there are parts of the country where access to groundwater is more important just because of geography. That's what they have there. So is this well functionality only predicting lack of access to a certain part of the country better than others? So it's like, I know that you are trying to proxy water access through the wells, but how representative that is in terms of the geography of the country? So you're mainly able to talk about whether water access in terms of the effects on migration of a specific subset of the country in terms of geography, on only that area or only that community. That might also be helpful to see. Yeah. Let me see what else. Okay. I mean, I have other minor comments. So I missed a little bit in the data section what exactly each water data is bringing to the table. So I mentioned there are two different water points data, for example. So is this one better to capture this and the one better to capture that? I think a little bit more reasoning that might be helpful. Some of your variables definition, I think that you add that to the presentation. So for example, this index here is clearly used by other papers, so that's why you use it. So that's helpful too. And also I would consider adding the mean of the outcomes and the main treatment, which is this non-functionality, which my understanding is that measuring months. So the number of months that the well is not functional. I would add the mean of that variable to see what is the average number of months that non-functional well happens. But yeah, I think that's all my main comments. I have others, but I think that you will address part of them, so I'll leave it for here. But thank you for your presentation and the paper.
Thank you, Carlos. Lucille, if you wanted to respond to any, and Carlos, if you'd be willing to send your slides, I'm sure that would be helpful. So Lucille, go for it.
Yeah, thanks, Carlos. And yeah, sorry, the paper changed a lot in between the version that you had and what I presented. So I know that's a difficult job when you're discussing something that's changed so much. So thanks. And I think you managed really well, even given the information that you had, you still made some really great points. So thanks. On the So I think the first point that you described is one of the main thing that I need to work on, is how different the agricultural shocks are from the shocks that I'm using to predict groundwater or wells failure. So I think I need to do more on describing it, but first, the geographical unit is different. So when I'm using climate to predict whether a well is functional or not, I'm always using the sub-basin as the geographical unit, because you don't know so how groundwater flows. It's really hard to know. And so precipitation shocks that can happen at one point in the sub-basin can actually impact a well that is at another point of the sub-basin. For agricultural shocks, it's really the water that falls on the field that matters. So when I'm controlling for climate at the for the agricultural channel, then I'm using the community as the spatial unit. The two are correlated, but still there's some difference. And also then the predictors for climate related wells failure are often lagged temperature, lagged precipitation, or lagged SPEI, which is less likely again to affect current agricultural outcomes. And interacting those lagged variables interacted with groundwater. And if you don't use groundwater for irrigation, then again, those shouldn't really affect the agricultural outcomes. So yeah, but I agree that I need to do more in terms of that. Then I think, I agree that I should add some agricultural outcomes as agricultural variables as outcomes. That's something that I need to do. I agree. I think, I should, as you mentioned. So I don't have the entire universe of wells in Ethiopia, and there's a question on how representative they are. Of course, I think using the two data sets is also where it's likely more representative, because one is going to be so the startup is mostly going to be wealthier communities that are trying to implement some ways of maintaining their water sources, whereas the second one is NGOs and government, and so those are more likely to actually go in the most remote and poorest parts of Ethiopia and try and report wells functionality there. So I think by combining the two, I might be able to compensate for the selection in the other. But I can definitely, this is my prior, I can show it with the data as you suggested. And then, yes, there are, so those differences in climate in Ethiopia are definitely important. And I want to do heterogeneity in like between whether you are a more arid place or not. You can still have, so it's not because your mean precipitation is higher that you cannot have drought also in those places. So you can still have wells failure in those places, but I can definitely show that better. And yep, I think I've answered most of what I wanted to touch on. But thanks again for the comments. They were good.
Great, thank you. Are there any questions from any of the panelists or any of the attendees? You're welcome to raise your hand and we can unmute you now. Yes, I'm going to unmute you.
Can you hear me?
Yes.
Yeah, thank you. That was very interesting presentation. I have a few with the Ethiopian Socioeconomic Survey. And if I understood correctly, you try to proxy the access to water using the wells. So how about just to supplement your finding, how you use the the drinking water accessibility using the survey. I remember they have that question, the spatial maybe to directly ask of the groundwater itself. First of all, it depends who constructed them. Some of them are not constructed by NGO or government. Some of them are constructed by the community. So if those community constructed groundwater are dysfunctional, I believe there is high probability that that community might also fix it. So there is this, I don't know, that still has some correlation with your estimation, but especially you mentioned that the deeper the groundwater is, the higher the probability of dysfunctional. So I have some effect on that. The other thing is, can you control for the distance to the nearest big city? Because this might have impact on the migration itself, and it has also an impact on the wells construction or accessibility to water. The survey has that information to the big city, but I'm not sure if the survey has information on distance to the near river or lake. Some of those rural area, especially in the south, they have rivers and lakes. So that means they have better access to water. Try to check if you have those information. And I know you have household size, but if you have the head of the household, if that is a man or a woman, it might have a huge difference. I know from the agricultural research, also from the groundwater, because if it is, I would assume that if the head of the household is a man, the functionality might be different. Yes.
All right, thank you.
Thank you.
So, first of all, I'm not using the survey as the main way to measure water access, because I think it's highly endogenous. So it's likely that the people that are gonna report taking more time have specific characteristics that are also correlated with migration. But I've done some correlations, and I do see that the people that report taking more time to fetch water, they migrate less. But that's not the main, that's not what I use as a main definition of water access because of endogeneity. Then I agree that wells can be constructed by different people, and I actually do see in the data, the wells data, that wells that are constructed by community are more likely to be functional than those that are not. For now, I wasn't using those information for doing heterogeneity later with the socioeconomic information, because there was this mismatch, as I was saying, on the timing of the world survey and the timing of the socioeconomic survey. But actually, discussing with people here, I realized that some of those are likely to not change across time. So if you were built by an NGO, the wells has been built by an NGO and it wouldn't change over time. So I think I can actually do some heterogeneity using some of those time invariant characteristics that I see in the wells data, but not in the socioeconomic data. So I agree that I can do and will do more on that. Then controlling for distance to the city and distance to rivers, I agree again that it's important. I have those household fixed effects. So for the river, I'm less worried, because if the river doesn't change its course over the time period that the socioeconomic survey happens, it's going to be taken out by those fixed effects. Same for the cities. So if no new city has been built closer to the household, then those cities are going to be taken out by the fixed effects. I want to do a heterogeneity on distance to cities, I agree, but I will not, I think it's controlled by the fixed effects. And lastly, yes, again, household size and household head gender. Again, I have those household fixed effects. So if the household head doesn't change over time, it's going to be taken out by the fixed effects. I have done some heterogeneity looking at gender, and I do see that households led by female are more likely to respond, which I think makes sense because fetching the water is a job mainly done by women. So that makes sense that those are also the ones that are responding the most. But again, everything is changing, and so I didn't put everything in this presentation because I'm not sure about everything that I've done, and I want to think a bit more about it before showing it to other people. But thanks.